Let's talk about camera calibration to figure out how our camera sees the real world around us and how we can map that onto our robot. So we talked before about how a sensing image like this gray rectangle on the right can take in points of light focused by a lens from the real world and map each of those points to a particular spot on the sensor. So how do we do this mathematically? Well, let's make a diagram first. You have a point in the real world here. You have your sensing plane over here, so this is your CCD or whatever sensing material you have. You've got some sort of a pinhole model in between. We use a lens in general, but it all comes down to the pinhole model in the real world. And we know that the light can only pass straight from the point here to one spot on the CCD. That's the whole point of the pinhole, that's the whole point of the lens, is that we can take light from one particular spot in the real world and put it in one spot on the CCD. So let's put a coordinate frame on this pinhole. This coordinate frame may look a little bit weird. It's not the normal X forward, Z up sort of thing. This is what we use with cameras. We'll translate this in just a little bit to something a little bit more familiar. But we'll use this coordinate frame for now, which means we can put something in the real world in this coordinate frame. So this point relative to the pinhole is in position XYZ here. And we'll have another coordinate frame on the sensor. So typically this is U and V, only two parameters because it's just a plane. We don't have any depth here. And so we can define any point on the sensor as U comma V. So there we go. Now we have something where we can take a point in the real world relative to the pinhole and map it onto the CCD. So what we're really talking about here is some matrix C that takes our XYZ point in the real world and turns it into a UV point on the other side. In a perfect world, this is a really simple mapping. This is basically what the focal length is. If you take the focal length, you divide it by the distance you are from the pinhole, multiply that by your XY matrix, you'll get your UV matrix. But how does this work in the real world? Well, you'll notice here that as our first attempt, it's basically the same thing. You have your f multiplied by your x and y, you end up normalizing by z there, and this looks very similar, but you'll also notice that there's a lot more spots in this matrix. It's a 4x3 matrix, not just one scaling factor. So why is this? Well, in the real world sometimes, the center of your coordinate frame on the CCD side, so on the camera plane itself, doesn't necessarily line up perfectly with the pinhole. In fact, oftentimes your origin plane is set to one of the corners of the image. That's not super relevant here, but the point is that sometimes the plane itself doesn't line up perfectly in the center of where the lens would refract to. So we need some parameter for that, and that's what this U0 V0 is in the matrix here. This is called a projection matrix, by the way, that we're filling out. And sometimes your pixels themselves aren't square. This is pretty common anymore. They're usually rectangular pixels now. And so we have to have some sort of a scaling factor here to go from just the focal length times some square image to instead the focal length times however many pixels per meter are in this CCD itself, so in this imaging sensor. And finally, the camera plane itself may not be perfectly aligned with the plane of the pinhole. So your UV plane may not be perfectly aligned with the XY plane from the pinhole. So we have one more parameter here called S, which is the skew factor. And we'll do some substitutions here, so each thing is only one variable, so alpha becomes f times m sub x, and beta becomes f times m sub y. And you take these 5 parameters here in this 3x3 matrix, and these become your intrinsic parameters for the camera. So these describe how your camera and lens interact and translate from some real-world coordinate system to some camera coordinate system, so the pixel locations on the camera plane itself. How do we find these parameters? We do intrinsic calibration. You may remember doing this with your DuckyBot earlier this semester. So what do we do in intrinsic calibration? How does this work? Well, briefly, if you have some sort of an image where you know exactly the size of the image, you know where it is, you know how everything relates to each other, like this checkerboard on the right-hand side of the image here, we know how big each of these squares are, we know how many squares are in the image, and it's relatively easy to write an image processing algorithm to find this checkerboard. So if we take a lot of pictures of this checkerboard, if we take pictures of it, medium distance, different angles, above a little bit, and then get close, and then get a little bit further away. We take a whole bunch of images with it. Then the checkerboard will pass itself across the whole camera in a bunch of different orientations. And so we can figure out where the real world pixels relate to the image plane by doing something like gradient descent or some sort of optimization method that we're not really talking about in this class. But we can use these methods to figure out the relationship between the real world there and the camera. And we can fill in these parameters in the projection matrix so that we can do our math and figure out where things are in the real world. So that's why you had to take so many different images with this checkerboard so that we could find all the possible angles and orientations and so on and map them all across the lens onto the imaging sensor. So this describes how we can take some point here in the real world with the coordinate system relative to the camera and map it onto a point on the CCD itself, so onto the imaging plane itself. But this is a really weird coordinate system, right? I mean, y normally isn't up, z normally isn't back, x isn't necessarily to the right. What we really want is some x forward, y left, z up coordinate system like we were used to from back when we talked about coordinate transforms. So how do we do this? What we've got here is camera frame coordinates going to camera plane frame coordinates using the projection matrix C here. What if we just do a transformation, just like we did back when we talked about coordinate transforms? So we take in robot frame, x, y, z, multiply that by the projection matrix and some transformation, so some three-dimensional theta and translation step, and we get our final UV answer in camera plane coordinates. This is going to look something like this. We've got your projection matrix times some sort of SE3 matrix, so rotations and translations, just like we've done before, times your XYZ, and you'll get your camera plane frame at the end of that. One thing you might notice here is that we're assuming we know the position of the object we're looking for in the 3D world, and we're assuming we're trying to find the object in the image. But our robots only have one sensor. They only have the camera. So don't we want it to go the other way around? Don't we want to go from the camera plane to the real world and say if something has a pixel coordinate here, it maps to this thing in the real world? Well, you may be tempted to try to do some matrix inversion here. And if you multiply these matrices through, you've got a 3x4 matrix here times a 4x4 matrix next to it. You're going to end up with another 3x4 matrix, and that doesn't invert. So what can we do here? Well, we can't really find a matrix that'll go from the two-dimensional coordinates on the left to the three-dimensional coordinates on the right. We'd be adding data. Or can we? What if we make some simplifying assumptions? So what if we transform from one plane to another plane? What sort of plane do we have in the real world we could transform to? Well, in Duckytown, everything's flat. You have a ground plane in front of you all the time. So what if we assume that everything is on the ground plane? How does this work out? Well, this means we take our 3D coordinate system here and we just flatten it. So we assume some constant z value, could be 0, could be some constant translation away from the camera, whatever, and we define this new xy coordinate system that's essentially a projection of the xyz coordinate system on the robot where z equals some finite number, some constant number. And now we're going from one plane to another plane. We're not adding any parameters, we're not adding any variables, we're just going from the one to the other. We should be able to do that. And on the robot, that means that we're taking this blue dot here that's in the XY coordinate system relative to the robot and mapping it to the yellow dot in the UV coordinate system on the camera. So we take our math here where we have our projection matrix times our transformation matrix, and let's just take the z components out of it. So we're going to remove the z variable in the robot frame because that's some constant we're going to deal with later. And then we're going to remove the rotational values that have to do with the z system here, that get multiplied by the z system here. And what do we find here? Well, we have our same projection matrix here times some smaller transformation matrix. So now we have a 4x3 transformation matrix times our xy coordinate in the real world, and we get our uv coordinate. So if we multiply this through, we're going to have a 3x4 times a 4x3. We can multiply that. We're going to have a nice 3x3 matrix here. This 3x3 matrix is called the homography matrix. It translates you from some real-world plane to some camera plane. So we have this homography matrix H. We can multiply it by our real-world xy coordinates to get our uv coordinates, or we can invert it because it's a 3x3 square matrix and the determinant is probably not 0. So we can invert it and multiply it on the camera plane side and find out the xy coordinates in the robot frame. And since we're assuming that all things have a constant z coordinate in the real world, we can just go ahead and add that z coordinate in later, so we know the 3D position of anything that could be in the real world from the camera's location alone. That's an assumption, it's always going to be an estimate, but as you can see in Duckytown, it's a pretty good estimate. And how do we get this transformation? Well, that's the other half of your calibration sheet here, where you have the coordinate system. If you know where the robot starts, and you know the pattern that it's looking at, you can find the mapping in the same sort of way by using optimization methods to map between one and the other to translate between the CCD plane there, the camera's sensor plane, and the real-world plane, ground plane in front of it. And this is how your DuckyBot knows where it is in the world. This is how it knows the obstacles around it, the lanes around it, and so on, by mapping from one to the other. So let's review. You use intrinsic calibration to figure out the parameters about the camera sensor and the lens, so how these relate to each other, so how something in the real world could translate into something on the camera sensor. Use extrinsic calibration to determine the transform between the real world and that camera system you defined in the intrinsic side. And we can then determine a homography matrix so that we can find the locations on one plane based on another plane. So from the camera sensor plane to the ground plane, for example. And that's one way that we can use a single camera as our only sensor in the real world and still get useful data out of it.